Thanks as always, Kimberly, for setting this up, by the way. You
You're
are the
welcome.
best. All right. Hello and welcome to the Weekly Space Hangout for Wednesday, March 20th, 2019. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about Ryugu is weird. Also, Bennu is weird. Star kicked out of the Milky Way, Pulsar kicked away from a supernova, and of course, This Week in Musk. Joining me this week on my camera right now, I've got Dr. Kimberly Cartier. Kimberly.
Hey, Fraser. Happy podcast day.
And Dr. Morgan Renberg.
Hey, Fraser.
Oh, there we go. Camera turned to you. All right. So before we get on to our special guest, I just want to give everyone a big reminder, of course, that they are running out of time to abandon Google Plus and make sure that they put all of their connections and community into the Weekly Space Hangout crew. So if you want to be a part of the amazing community, go to wshcrew.space. There's, I don't know if the forum is set up yet, but you can get access to the Slack community that's going on here. And of course, you then get to be an executive producer of the show. And for example, this week, we've got an amazing guest. It all happened because one of the executive producers at the Weekly Space Hangout crew set the whole thing up. So if you have guests that you want to see on this show, join the crew, become our executive producer, and then organize the guests that you want to see. It's how it works. All right. Speaking of special guests, let's get into it. Let me find my special guest. All right. Joining me this week, we've got Michael Zemcov. Michael, welcome to the Weekly Space Hangout.
Hi, Fraser. How are you doing?
Awesome. We were talking about this beforehand, that sort of between the two of us, with your sideburns and my beard, we form one complete beard between the two of us. So I think that's great.
Yeah, it's. I don't wear this facial hairstyle very often, so you caught me at a weird time in my life.
So who are you? What do you do?
So I am an assistant professor at the Rochester Institute of Technology. I do what I lovingly refer to as experimental cosmology, which means building experiments to do cosmology. So, of course, when you do that, mostly that involves building telescopes because this cosmology is astrophysics. But I like to think that I could do other things too.
And specifically, you're working on a mission that we want to hear all about.
Right. So I am a co-investigator on SPHEREx, which is the latest NASA mission that was just selected about a month ago to go and make a spectroscopic map of the sky in the near-infrared wavelengths with the idea of trying to understand things like inflation and galaxy evolution and where water ice comes from in the galaxy, things like that.
So let's talk a bit about sort of the wavelength. You say near infrared. So what is that good for?
So near infrared, in this case, we're talking about 0.75 microns, which is just at the very red end of what humans can see, out to about 5 microns. And it ends up that stars emit most of their light at those wavelengths. So just by sort of cosmic coincidence, or however you want to think about it, when you make images of the sky at these wavelengths, what you're really doing is seeing a lot of direct emission from stars, whether that's in our galaxy or other galaxies. So that's really the genesis of why would you look in the near infrared? Well, it's where a lot of the light is in the universe.
Right, especially as so much of the more distant objects are redshifted away from us. I mean, it's like the cosmic microwave background radiation that used to be red. Now it's microwaves, thanks to the expansion of the universe. And so you're taking advantage of that same redshifting.
That's right, exactly. And so a lot of what we're doing is actually into the universe about redshift 1, which is sort of like the universe when it was about 2/3 its current age. So we're kind of mapping out the structure between us and that distance away.
And so what specific objects are you hoping to be able to see at that distance?
So the byline that I use, which is oversimplifying things somewhat, but I think kind of gets the sense of it, is that SPHEREx is going to be able to map the three-dimensional position of every galaxy that matters out to that redshift one. Every galaxy that's above a mass, let's say that's similar to the Milky Way, we'll be able to figure out where it is, with about % accuracy in three-dimensional space.
Just to give people that a little bit of context, if they don't speak redshift, what is redshift 1 in terms of billions of light years, which is clearly a much easier thing to wrap your head around?
Right. So redshift 1, people can correct me on the chat and do the math, because I'm not going to be able to do it in my head very well, but it's something like 9 billion light years, I think, like some
Right.
distance.
Right. So we're essentially going to build up a three-dimensional map of all of the large galaxy structures out to this distance of 9 billion-ish, give or take a few billion light years away. And I mean, is that like an interesting time in the universe? Because, of course, when you use a telescope, you're looking backwards in time as you were looking farther away. What is that time? What is interesting about that time?
Right. So it ends up that what we're doing really is we're not so interested in exactly where that brick wall is. It's the three-dimensional structure of the universe between us and that distance away. So the concept here is we know the equations that govern how matter and structures form in the universe, and we've done a pretty good job of showing that not our team, but science in general, humanity has done a pretty good job at showing that we can trust those equations as a description for what does the universe look like. And it looks like, on the largest scales, kind of like Swiss cheese, where it's got galaxies living on these sort of walls and then big voids where there's really not much of anything. The idea is that we have sort of the math, the theory that describes that quite well. And what we can do is kind of turn things around and say, okay, well, if we understand how structure sort of evolves over time, maybe we can use that understanding to say, what were the initial conditions? What were the sort of inputs that made the distribution of matter the way it looks today? And if you kind of do some quite complicated math and stare at it for a while, what you figure out is that that three-dimensional structure is dictated to a certain extent by what was happening in the very, very earliest moments of the Big Bang. We call this period inflation. So this was the time where microscopic sizes were suddenly, exploded into macroscopic cosmic scale objects, which basically took sort of fluctuations at the quantum mechanical scale and exploded them into giant cosmic sized structures that were basically the seeds for where galaxies form in later times. Inflation was very, very early in the cosmos, tiny fractions of a second after the Big Bang. And it was posited in the 80s to kind of explain some peculiarities about how the universe is basically so homogeneous. You look in one direction, you look in the other direction, it looks like it's uniform, but there's no way that the universe could have talked to itself in that time, just because where we are is the first time that light would have been able to interact. So the concept of SPHEREx, at least one of the main science cases we're pushing, is that if we can make a really good three-dimensional map of where galaxies are, we can kind of back out what were the initial conditions and then say something about inflation, how that happened.
Right. And I mean, we covered in excruciating detail both the discovery or the announcement of primordial gravitational waves and then subsequent overturning of the results. So we know the hunt is on for other lines of evidence to help demonstrate that inflation is a thing. So let's say that things proceed as you hope. When will your mission launch and sort of give people sort of a sense of scale here? Is it James Webb sized, test sized?
No, it's desk size, I would say. So we have a 20-meter telescope, or 20
nice.
centimeter telescope. It would be a lot more if it was 20 meters.
Yeah.
20 centimeter telescope. So 20 centimeters is what, 8 inches or so? So this is like a dinner plate size kind of thing. And the interesting thing is that if you're trying to do the kind of science we're trying to do, you don't care so much about angular resolution. You care about how much light can I gather and how much spectral resolution, how many spectral elements can I get across the wavelength range. So SPHEREx is, yeah, basically the size of a desk, a big desk, and it has these sort of umbrella shades that let it passively cool because it's looking at the cold radiation from space. You know, those make it look a little bit bigger, so maybe like small car size. But I think the actual sort of instrument package itself, the telescope, is like the size of a suitcase.
Right.
That's the kind of size to have in your head.
And then it is going to survey the entire sky slowly, as you said, gathering large amounts of photons as best it can over time.
That's right. So it's in a terminator orbit, which means it follows the sunset sunrise line of the Earth. And so it's looking basically at right angles to the sun always. And it basically just, you know, in 6 different spots on the sky, points and shoots and takes an integration. And then the orbit moves on and it points and shoots and takes an integration. And, you know, over time, if you pick your pointings, you know, intelligently, it lets you build up a whole map of the entire sky in about 6 months.
And what is, like, I mean, you mentioned potentially being able to connect inflation to the current state of the universe a little better. What are some of those big questions that you're hoping to answer?
So inflation, I think, is one of the unique ones that is very interesting because they really get at it. The other two that we're sort of pursuing in the team are to sort of understand the evolution of galaxies from, you know, the epoch where galaxies were first forming down to locally. And the way we're going to do that is through intensity mapping, which is a relatively new method that basically doesn't treat galaxies as individual point sources, but it looks at sort of statistical fluctuations in images. So you can think of this as, you know, taking a picture again of like Swiss cheese and saying, okay, well, I know what the statistics of Swiss cheese are, so I can say whether the universe looks like that kind or whatever. So that's another one of the science cases. And the hope there is we're really going to be able to understand, for example, the formation of stars over cosmic history. And then the third big science case is to look at basically protostars and very young stars and look for water ice around those sources. And the idea there is to understand, okay, well, where does water ice come from? We know that there's a lot of water in the universe, and we know that, you know, some of the planets are very wet like Earth and some planets are very dry, apparently like Jupiter is. Where does this water come from? Is it coming from comets like people think, or are there other reservoirs? At what point in the history of stellar systems does it sort of get in place? That kind of question.
That's amazing that you'll be able to see all that with a 8-inch infrared telescope in space. I mean, that, you know, that being in space really helps with those observations.
It buys you something.
Yeah. But I really love these ideas of fairly small concept, very specific focused instruments designed to answer some of these questions in sort of the tightest, best package. And this just sounds really exciting. So good luck. When will we see it launch?
So the current launch schedule puts us in late 2023 for launch, which is actually really, really soon. But, you know, we have a pretty mature design. So I think we're going to spend a few months kind of ironing stuff out, and then we start building. And then the notional mission is 2 years. So we should be having results in maybe 2025. But one of the really, you know, important legacies of SPHEREx is that we're going to make the data public sort of like right away, as quickly as we can, because it has a lot of synergy with things like JWST, where we will find interesting sources that perhaps would be followed up. And so, you know, a big push from NASA and a big thing that we want to do on the team is to get the data out as soon as we can, because, you know, an all sky map in near infrared at these kind of spectral resolutions is really valuable for all kinds of science.
Amazing. So Michael, if people want to find out more, where should they go?
The website is spherex.caltech.edu. And I think that's probably the best resource right now, but NASA will be putting out press releases as thing goes along.
As they do. And if people want to follow what you're working specifically on, where can they find out more?
Oh, just Google search me and you will find me. I have websites at rit.edu.
And a fairly unique name.
Yes, ZEMCOV.
Perfect. All right. Well, Michael, thank you so much for joining us today. Good luck with your mission. Say hi to Brian Coberline when you're around RIT. He's a regular panelist here on the show. So
great. Thank you so much.
All right.
I will.
Take care.
All right. Take care.
All right. Moving on. Let's get on with the news. Who will show up on my screen first? It's Morgan. Morgan, what do you got?
Asteroids. They're weird. And
I think you just stole Kimberly's,
You totally
thunder.
stole
Yeah.
my intro.
Asteroids.
Oh, wow. Ouch.
They're weird.
Yeah, today was kind of a strange day because there was just this like dump truck load of new science released about both Ryugu and Bennu, and I drew the Ryugu end of the stick. So let's talk about what Hayabusa 2 has been finding. We might remember from a couple weeks ago that they performed their first sample collection by kind of smacking into the surface and jarring loose some material that got scooped up into the spacecraft and will eventually be returned to Earth when Hayabusa 2 swings by in a couple of years. But it's been there for a while now, much longer than OSIRIS-REx has been at Bennu, and they've been sort of just orbiting it and imaging it for forever now. And they have this incredibly detailed map that maps every feature on the surface of Ryugu down to a scale of 2 meters. And then they've also been making gravity estimates of the asteroid by letting the spacecraft sort of drift under the influence of Ryugu's gravity to measure how much mass it has. And if you combine mass with a detailed estimate of shape, what you can do is derive a bulk density, or sort of the average composition of the thing. And what's really shocking here is how low that density is. It's measured at about 1.19 grams per cubic centimeter. And to kind of put this into context, water is 1 gram per cubic centimeter, and pure rock is like 5 or 6 grams per cubic centimeter, depending on the composition of the rock you're talking about. So here we have something that's much more like water than it is like rock. But here's the sort of the kicker, is they've also been using their spectral instruments to measure the composition of Ryugu, and they found it to have almost no water content. So that's
So it
kind
has
of
the
weird, right?
density of water with almost no water.
Yeah, so there's basically no material that naturally occurs that has those two qualities. And so what this means is that Ryugu is not a solid object. What does have these qualities are a bunch of rocks at density 6 and a bunch of free space at a density 0. And if you average them together, you get 1. And what this tells us almost is you can almost just kind of do the dumb calculation and say there must be like 6 units of empty space for 1 unit of rock, or 5 units of empty space for 1 unit of rock, to average it out to 1. And that tells us that Ryugu is incredibly porous and is really what we'd call a rubble pile.
Mm-hmm.
And I think we're finding this out more and more as we see more and more asteroid-like objects. But to be this loose is really striking.
I just like imagine this. I mean, I'm not sure whether it was ever a rock, like, when we imagine like an asteroid tumbling through space, but then it's got smashed by other asteroids in its history, and then it sort of blew apart, fragmented, then mutual gravity sort of pulled it back down together, and it got smashed again and broke up, and it's just getting like churned up into this accumulation of rock. I mean, It is such a different concept of what we would have thought an asteroid to be like. It should make asteroid mining a lot easier because you literally just have to scoop them up in with a bucket.
Yeah, a couple weeks ago when you were in Costa Rica, Pamela brought us this story about how if we tried to like nuke an asteroid, it doesn't work because you blow it up successfully, but you can't fling that stuff far enough away that that mutual gravity doesn't pull it back together. And I think that's probably sort of what we're seeing here is the scientists estimate that an object of this size should have a destructive collision, something like every 100 million years. And so even if it's been lucky and that hasn't happened in the last few 100 million years, it's been totally broken up multiple times over the course of its history, only to drift back together over into this sort of, but not with enough speed to kind of crunch down into a solid object.
Now, one of the sort of interesting pieces of research that I had noticed was that this low amount of water actually causes some issue with the source of water here on Earth.
Right. We've thought for a while that one method of delivering water to Earth was through the impact of comets and asteroids. That's not necessarily the only way that you could have gotten it. But if you think, we often think of things like asteroids as leftovers from the beginning of solar system. And if comets didn't deliver water, then the idea is that when the Earth accreted out of a bunch of stuff that looked a lot like asteroids, that it would have had a lot of water already built in. And then that water kind of bubbled to the surface in the early part of Earth's history and gave us the ocean. And we know that there's like 50 times more water in the Earth's crust than is in the oceans. And so we don't need comets. But what we do need is wet material at the beginning of the solar system. And just because these asteroids are dry now doesn't mean that they were dry at the beginning of the solar system, but it does sort of make you think a little bit more about what might have been going on.
Well, I'll tell you what, there are other asteroids that have water.
But are they weird?
Yes.
So the Hayabusa 2 results also noted a couple of other sort of strange things, that even though the collision history would suggest that Ryugu should sort of be totally remade every 100 million years, the surface is incredibly dense with craters, and they estimate that the surface gets resurfaced by craters just every million years, which gives you a sense of how rapidly it's sustaining impacts. And then it has this really sharp feature at the equator, this like ridge-like feature. And the hypothesis here is that in the past, Ryugu was spinning much, much more quickly. And as spinning things do, they tend to bulge out at the equator. The Earth's radius at the equator is much larger than its radius at the pole. And if you have an object that isn't solid, like say a rubble pile asteroid, you would expect to see more and more of this bulging. So that tells us that it probably was spinning quickly in the past. The question is, why isn't it still spinning quickly? And they haven't really answered that question. Probably the fact that it's a rubble pile plays some role into that, because you have a bunch of pieces that are moving in slightly different directions from one another, and over time that kind of internal friction would tend to slow it down. But we see very strong evidence that it was moving quickly in the past, and yet it's moving very slowly, rotating very slowly today. And again, that just means that there's these processes that are going on over long periods of time that we really don't know how to account for with the physics we understand yet.
So a couple of interesting comments. Kyle Carmichael is noting in the comments that, to me, something that would be repeatedly broken apart should have lost its volatiles, like water from the impact when it was dispersed by the solar wind. So could that be part of the process, that the thing gets smashed up, showing new water to the surface that then gets blown away by the solar wind?
Absolutely. You could imagine that this could happen either just what you said, is that you sort of break it apart and show shiny new material, and that material evaporates away. You could also imagine the collision energy could be quite significant, and it could, on impact, basically boil away a lot of that material as well. And so I think what all of this is pointing to is that we need to better understand how likely these big disruptive collisions actually are. Because if every asteroid or many asteroids have gone through these disruptive collisions again and again, then they're a lot less useful as markers of what was going on in the early solar system than we sort of typically assign asteroids. And maybe we need to think more about comets and Kuiper Belt objects farther away, which we know must have been colliding a lot less frequently because space is just so much bigger in the outer solar system than it is in the inner solar system.
All right, that's pretty weird. Kimberly, weird it up one more notch.
Yeah, I take Ryugu's weirdness and I raise you Bennu. Bennu, another asteroid, another rubble pile asteroid, has been playing host to OSIRIS-REx since December. And just this week, first science results came out, sort of like right on top of the Hayabusa results. And it's weird too, because it's an asteroid. So some of the not weird things, its size, its shape, its rubble pile-ness, its composition, those are all pretty much what the mission scientists expected, which is good. Not everything needs to be a surprise. One of the things that was a super big surprise is that Bennu is ejecting particles as like plumes or jets, like a lot, like
Right.
very, very frequently. They
like a comet does?
Not quite like a comet, almost like impact ejecta spraying outwards, but without a visible impact. So what happened is they were looking through their navigational images back at the beginning of January as they were about to go into orbit, and they noticed that there were some really strange, like bright spots off the limb of Bennu. And after processing and figuring out what's going on, they realized they were real and that they were present in more than one set of navigational images. They came up with some like quick data processing algorithms to figure out what's going on. They realized they were actually like rocks coming off of the surface of Bennu, and they started monitoring it for like a month straight, and they caught 11 separate events, like discrete events where particles were being ejected from the surface of the asteroid. And these particles are like anywhere from like centimeters to tens of centimeters in size. And they're going at a wide range of speeds, anything that could just like, gently lift off and fall back to the surface like rain. Some of them actually entered into orbit around Bennu. So it's creating like a natural satellite system, like self-creating its own satellites. Good news is that the craft is not actually in any danger. They're pretty sure it's not going to like get bombarded by rocks while it's in orbit. But they've never quite seen something like this before. There are some asteroids that are called active asteroids where there is some activity going on where it's releasing material from the surface, but not that we've observed to this degree and such that the particles are entering orbit and creating this satellite system. That's a completely new thing. They were not expecting to see it at Bennu at all. There was no indication ahead of time that something like this was happening. It's super weird.
That is really weird. It's kind of amazing that that it did it 11 times. Discrete events.
This is a real thing happening all the time, like 11 times in a month. And some of these events had like hundreds of particles being released at one time. So this is not just a freak happenstance that we observe. This is a thing that must be happening frequently.
So is the idea here that this is micrometeoroid impacts on the surface?
They actually have absolutely no idea what's going on.
Like Bennu is tiny. You wouldn't expect.
Bennu is super duper tiny. It's like it's less than 300 meters across. A couple possible theories include. So we said that it's a rubble pile. It's actually about 60% porous inside. It's very empty, and and it's rotating faster and faster. Its rotation is accelerating. So one thought is maybe the increase in rotation is grinding some material together inside that eventually gets flung out, or things shift around just enough on the surface that it knocks something off, or it could be some sort of micrometeorite impact or an impact from some of that particle rain coming back to the surface and knocking off other material. There are so many different theories. Actually, they have no idea what could be causing it, where the events happen, when they could be happening. It's like they've known about it for just a couple weeks, and they're still trying to like wrap their heads around the fact that this is actually happening at Bennu, and they have to deal with it.
So you talked about the plumes,
They're sort of going. They're settling in on the terminology. I've been calling it jets, just so I can say Bennu and the jets and be funny like that. But it's more just like spray. It's like particle spray coming off the surface.
But that's not. I mean, there were a bunch of other pretty interesting announcements made.
There were. So this
NASA.
Bennu thing, it's really weird. Okay, so the other sort of thing that's really important to the mission is what the surface is like. We saw with Hayabusa and Ryugu that the surface of Ryugu was not what they were expecting. It was much more bouldery. They had no idea if they could actually do their sample grab maneuver. It worked. Yay. Now we're running into the same problem with Bennu in that before OSIRIS-REx launched, when it was still being designed, the ground-based observations of Bennu suggested that the surface was relatively smoothed and probably covered in like centimeter-sized gravel. And so they designed the mission for that kind of surface. Now that they're really close up, they realize that that's really not the case. Bennu is almost entirely covered by boulders that are meters to tens of meters in size. I think the latest count was something like 200 boulders larger than 10 meters. And the largest one was something like 60 meters across. So that's an issue.
Right,
They designed
different
OSIRIS-REx
from the
to do
Ryugu surface, right? When you look at the Ryugu, it looks like this pulverized gravel.
Yeah, and I mean, Ryugu still has some boulders, but they're more like a couple of them that are a meter or 10 meters. Bennu is like almost entirely covered by these giant boulders. And they designed OSIRIS-REx to do a touch and go sample grab, and they gave it something like a 25-meter radius area to target. That whole area needed to be hazard-free of boulders and steep slopes and such for it to work. And the newest estimates are that there are no patches of Bennu that are 25 meters across that are free of hazards.
Oh no.
It doesn't exist. The good news is that there are smaller patches, something like 5 meters across or something, that have this sort of finer grained gravel or regolith. And the navigational systems are performing better than expected. So they do think they will still be able to manage to hit that smaller target area.
But I just imagine that, right? Like you imagine the spacecraft having to sneak down in between
all the
field of boulders
to
get to that soft, loamy soil, and then pull a sample and bring it home.
There's like half a dozen sites that could work. There's gonna take much more, many more pictures of the surface to make sure that they get the right sample site, because they have so many fewer to choose from than they thought they would.
And they should be able to match the rotation of Ryugu, right? I mean, its gravity is so low, the synchronous orbit must be very low, and just kind of hover there until they're comfortable and then just do it.
One would hope. Yeah, their orbital maneuvering is actually really cool, and it's doing really, really well. It's in one of these unique orbits where the pull of gravity from Bennu is exactly balanced by the push from the solar wind. So they actually haven't had to do any orbital maneuvering at all since they've gotten into orbit. They manage this like perfect balance in this orbit. So if they need to hover or adjust anything to get that perfect sample site, they have plenty of leftover fuel because they haven't had to use any.
Amazing.
Bennu's so weird. Particle jets coming off an asteroid. What the heck, man?
I do feel like particle jets is a little
I totally
weirder.
win. There's like a dozen of these
that is
out of all of the asteroids, and we picked one.
Yeah. But I think that also sort of brings us back to Morgan's preference that we can somehow visit them all. That now that we're seeing how different and how far they are from what we expected, we really need to go and visit all of them.
Yeah. And you know what, Morgan? This asteroid has water. It has plenty of it. Its mineralogy is like, look, I got all the water. I got all the aqueous byproducts. Take that, Ryugu.
And I should fall on my sword. Everybody in the chat saying that rocks weigh like 2 to 3 grams per cubic centimeter, which is totally right. I was thinking more of metals being higher than that. But even so, we're much closer to water without any water.
Earth is like 5-ish.
Yeah.
Yeah, but it's got all that iron in the middle. That's what was confusing me.
That's the number that It's
About
okay, Morgan. That's the number that sticks in my head as well. I think about planets and like their bulk.
Yeah, if you'd asked me
It's
like
okay.
what is the density of rock, I would have guessed in
It's
the
the
5
foibles of an
range.
astronomer versus a geologist.
It's all
Yeah, I don't want to actually have to touch the things.
it's all just metal.
Not digging in the dirt. Oh,
yeah.
come on.
All right, so I'm going to show
What do you got, Fraser?
like the coolest picture. And this is an image. Let me see if I can bring this up here on the screen here. All right, and I'll share this with my co-host so they can see it as well. So this
Picture's
is
just nuts.
This is amazing. So what you're looking at here, this is an image of a supernova remnant. This is sort of the big circle. Apologize to the podcast listeners. This is a supernova remnant. And then what you're seeing down in the bottom left-hand corner is a pulsar that has been ejected from the supernova explosion. And you can sort of trace the trail of the supernova right back, or the pulsar right back to where the supernova happened. And so astronomers think that this supernova happened about 5,000 years ago, and the 10,000 years ago, sorry, and about 5,000 years ago, the pulsar pierced this outer sort of shell of the supernova remnant and is continuing to move, and its trail is about 13 light years long. And so what the source of like why it's moving so quickly, and that's still a little unclear, but one idea is that the pulsar was in some kind of binary arrangement with another star, and one star suddenly vaporized and the other one was kicked out of the of the system, or possibly that the pulsar had, when the star went off, there was some kind of asymmetry in the star, and when it detonated, then it just got this gigantic thrust and away it went. And so it is, the pulsar is about 6,500 light years from Earth, and it is just moving and moving and moving, and it's just amazing. It's going 700 miles per second, which I don't know what that is.
Absolutely
in
crazy.
10,000 kilometers a second, which is really, really fast.
I mean, like, we've seen a couple of these pulsars, like, having been ejected from supernova remnants, moving at like a fifth of that speed or something like that. I mean, it's not unknown, but it's super rare, and we've never seen anything moving this fast, like from this phenomenon. It's really weird.
Why does the pulsar move so much faster than the shock wave? I assume this bubble we're seeing is the supernova shock wave.
Yeah.
Like what kicks the pulsar, which weighs a heck of a lot more than gas molecules, to go so fast?
Well, I mean, they've got to go through the interstellar medium. These are Paul questions for sure. So I'm just gonna oogle over the picture.
It's just a bananas picture.
Yeah. And
one would think that at some point there's some sort of braking mechanism on the outward shock wave that slows it down, that the pulsar can just like pierce through.
Yeah.
One would think that there's something like that.
Much more momentum.
This is why we need Paul.
Yeah, exactly. And so just in the same vein, I wanted to show you also another interesting story that's sort of in the same area, which was that a star was ejected. A hypervelocity star has been ejected from the Milky Way. And we see this happen more often, but it's just amazing to sort of think about the speed that these stars are going. So this one is going 500 kilometers a second, so that's 1,000,000 miles an hour, twice as fast as other stars. And so sort of this is the most recent one. A few others have been found. I think this was originally found thanks to Gaia. And so, of course, one of the things that the Gaia spacecraft does is it finds all these amazing objects. And the actual source of these hypervelocity stars is still a bit of a mystery. One idea is like with that pulsar, that you've got this perhaps a star in a binary arrangement with another star. One star goes supernova, and the other one is now without an anchor, and away it goes, leaving the galaxy. Or some kind of interaction with the supermassive black hole that's at the heart of the Milky Way. And so you can imagine a star getting too close, getting caught into a three-body interaction with the stars that are buzzing around the center of the Milky Way and getting kicked out. So it just shows that there are these dramatic natural events that can send stars on intergalactic trajectories out of the Milky Way, and I just love that.
Velocity stars are super interesting. I mean, like most of the ones that we've detected, we can actually like track their path backwards towards the bulge in the center of the Milky Way, which is why we're like, oh yeah, totally the supermassive black hole, totally kicking stuff out. That's what it does. This one came from the disk.
Yeah,
like,
so
it came from a spiral arm.
Yeah, so they
which,
weren't, they were quite surprised to see that this hadn't come exactly from the galactic bulge, and so the source of this one could be a much more complicated interaction with other stars, perhaps with, passing through
maybe a star cluster.
Yeah, exactly. Some kind of star cluster or
weird
globular
intermediate
cluster.
mass black hole. I don't know. This whole area, this whole like spiral arm that it supposedly came from is like obscured by dust, and we can't actually see anything that's in there.
Yeah.
So.
Yeah. John Yogurt is saying, is Fraser going to cover how you regularly plagiarize, summarize, and misquote your own words? I don't know if
we all.
Yeah, I know. I don't know if people saw this on Twitter. So I got accused on my YouTube channel again for like the fifth or more time of quoting word for word, plagiarizing word for word an article that was written on Universe Today. And
I remember back being in like school, like in high school or something, and it was a big no-no to like use something you had already written for something else. And I feel like they were not adequately preparing me for the realities of the real world, where I want to use the same thing as many times as possible.
Yeah, exactly.
Sure. I mean, like even academic papers, when you write like more than 5 exoplanet papers, you have to like viscerally stop yourself from starting with like when the Kepler Space Telescope launched in 2009, and every paper starts
that,
the
like,
same
perfect,
way.
You've written that perfect description of your instrument or your methodology. You want to keep using it, but you do get flagged by journals who use those same kinds of automated screens that our high school teachers were using, saying, "Hey, you're plagiarizing this thing," and then you realize, oh yeah,
it's my words, I wrote them.
Yeah, and so I actually did that today. I released a new video today about why it's so difficult to land heavy payloads on Mars. I took the script and put that on Universe Today as an article. I embedded the video onto the script, and now I anticipate being accused of plagiarism when people see my article.
The fun thing is that when you do it that way, when you do the video first and then you write the article, you can edit out all those silly things that you didn't mean to say and all of like your little verbal twitches.
I actually did edit briefly. I fixed a couple of words in the actual article.
Ooh, that number was wrong. Let me fix it.
Yeah, I said that the space shuttle's tiles were ablative, but they weren't. So I was able to edit the script so that was perfect. But yeah. So,
at what point are you going to just be making videos by editing together your old videos? So that you never have to shoot more footage.
It's a matter of time. Yeah. But anyway, yeah. So I get accused of plagiarizing articles written by Fraser Cain for stealing them word for word from my videos. But obviously I made them say at the same time.
That guy's smart. He knows what he's talking about.
Yeah, yeah, exactly.
Why wouldn't you plagiarize Fraser Cain?
All right, so I've got one more thing that I want to show people, and this is really cool. So just to give people an update on Musk, this week SpaceX warned the people in Boca Chica that they were going to be testing the new SpaceX Starhopper. And so we've been seeing sort of updates this week with them attaching one Raptor engine to the SpaceX Starhopper. This is, of course, the scaled down version of the Starship.
Is that the thing that fell over?
That's the thing that fell over, yeah. So it's
okay.
So it's fixed. And they just gave a warning to the people in Boca Chica that they're about to, and they've sort of clearing roads around the area to make sure that they, it's safe, and they are hoping. I've heard as early as like tonight, we should see a first test. And
someone post in the comments if you've seen it yet.
Yeah, if it's happened already, or if it's about to happen. Yeah. And of course these first tests will likely be nothing more than the thing lifting off meters, and then coming back down to the landing pad. The other
As long
thing
as
that
it doesn't fall over.
Yeah, the other
Again.
thing that SpaceX shared this week, which I really love, was they shared them showing off the hexagonal heat shield. Did you guys see this?
No.
Yeah, I was kind of confused
Yeah,
by
I'll
this.
show you this
Is
if
that
you missed
the
it.
hexagons? Because they made this big deal about how the heat shield was just going to be basically steel that was being cooled. Are these hexagons the thing that was made of steel?
Yeah, so let me go back and sorry, there's noise here. I'll turn the noise off. All right, and we'll go larger here. Okay, so they've got a bunch of blowtorches that are on the hexagonal steel tiles that are on the outside of the Starhopper. This is
And why are the
the
edges of the hexagon not heating up as much? Is that where the water is? Where
that
the coolant?
Right. So all right. So let's just sort of approach this in a couple of ways. So the first thing is that what the outer sides of the spacecraft are going to be made of is this stainless steel, as opposed to the original plan that they were going to be building it out of carbon fiber composite. And this Elon Musk had said this was the delightfully unintuitive strategy. And it turns out that stainless steel is very strong and has a interesting way of moving the heat around. And so instead of necessarily trying to get it cool down completely, if you can sort of time things will heat up. You'll get the heat away from the windward side of the spacecraft so that when it actually makes it and slows down and gets to the landing, it won't have cooked everything inside. And then the additional thing that they're planning to add is that the stainless steel will have tiny holes where it will bleed fuel, and the methane fuel will come out of these tiny holes and further carry away some of the heat that's being that's sort of building up on the spacecraft. So nobody's ever tried this. This is so different an idea than really any landing system that's ever been figured out before. And so I think I definitely think this falls under delightfully unintuitive, and in fact game changing if it works. So
Yeah, anything to get rid of those ablative heat tiles that need to be replaced, space shuttle style, or even like Falcon or like Dragon style, where you have that material on the bottom.
Yeah.
If you're going to fly this day in and day out like they want to, you need something that is going to not need to be refurbished between flights.
Yeah, the on the Dragon capsule and on, like, for example, the Mars Curiosity, they use this stuff called pica. I forget the exact name, but it's this very, it's an ablative heat shield that you have to replace it every time you want to use it. And while this one, in theory, you will be able to re-enter the atmosphere, land, and do it again without having to do serious sort of rebuilding of your spacecraft. So I think this is going to be very interesting if they're actually able to pull this off. Oh, and a bunch of other SpaceX rockets launched in the last couple of weeks. But I mean, that's really boring now, so we don't need to report on that. So yeah, they call it transpiration cooling. Starship needs to be ready to fly immediately after landing, zero refurbishment.
Prove it's possible. I'm
yeah,
looking forward to it.
Like it's the.
And that's what it's going to take to make routine spaceflight.
Yeah, if they can pull that off, it will be mind-bending. So anyway, this week in Musk. Hopefully next week we'll be able to report on the beginnings of the hop test. We're still a long way away from the Starship flying, but still super exciting. All right, Morgan, you're on my screen. Tell me something interesting that you're working on.
Yeah, I just had a video come out for SciShow Space looking into different ways that we might be able to detect alien life without using SETI. So what signs might we see of intelligent life, of unintelligent life? There may or may not be some megastructures involved. So check that out over at youtube.com/SciShowSpace.
I watched the
I'm making
video,
a
I
face.
enjoyed it, and I knew it was yours. I could just tell. In fact, there were some ideas in there that I've reported on technosignatures and biosignatures all the time, and there's a few ideas in there that I had never seen before. So that was really cool to go look.
Yeah, check it out.
Yeah, that's awesome. So yeah, definitely check it out. Kimberly.
Also, I've spent my week knee deep in OSIRIS-REx and Bennu, which I've talked a lot about tonight. So you can read all about that on eos.org. And then tomorrow there's going to be a really cool thing about fossils that you can also read about, but that's all I can say about that right now.
So you're going to have to follow her
It's a
on
secret
Twitter
until tomorrow.
and the EOS RSS feed to
Yes.
see the moment this new article
If you're
drops.
not following me on Twitter or following me on eos.org, what are you doing with your life?
There you go.
I don't know.
All right, so I've got just a couple of things. Three things. One, I just posted a new video all about landing heavy payloads on Mars. I'm really proud of it. Check it out. Two, if you're in Calgary, I will be giving a talk tomorrow at 7:30 at the Calgary. I don't even know where I'm going to be giving the talk at. Somewhere in Calgary.
What are you talking about?
I'm going to be talking about cool new telescopes that are coming out. So that'll be tomorrow, 7:30, Calgary Science Museum.
Space telescopes or ground telescopes?
Yes.
Yes.
Yeah, I talk about it's this sort of topic that I love to cover on a regular basis. I call it the rise of the super telescopes, and sort of just it's all about the new big telescopes. You know, the extremely large telescope, the James Webb, LUVOIR, things like that. I should just get the name here. Hold on. I will be at 7:30 at the University of Calgary Science Theater, March 21st.
Oh, I like the sound of a science theater.
Yeah. Do you guys have one? And the last thing that I want to mention is on Saturday, it is going to be the 20th anniversary of me founding Universe Today. So I founded Universe Today March 23rd,
Congratulations.
1999. And so this will mean that I've been doing this job of space news reporting for 20 years.
What's the coolest story that you've covered in 20 years?
Personally, I think going to see the launch of OSIRIS-REx
That was a lot of fun.
in Cape Canaveral. I think that's the most just like the personally bucket list thing that I've gotten a chance to do. Yeah, that was definitely it. But I mean, in 20 years, I've had a chance to talk to what's got to be dozens of astronauts, space scientists. I've been to all kinds of really cool locations. I've been to Iceland. I have been to Cape Canaveral several times, and it's been wonderful. So thank you everybody for following along for the work that what I've been doing for 20 years. Thanks to all the patrons. And if anyone is on the fence, should become a patron. I've been at it for 20 years. That's my commitment, and I will keep at it. I'm not going to retire.
Do it.
It's hard to can't retire when you found what you love. So, thanks everyone for 20 years. All right, and Morgan, Kimberly, thanks for joining us this week. Thanks to all the moderators for running and keeping the chat going. Thanks for everyone watching us live, and we will see you all next week. Let's get the gallery view. There we all are.
Happy podcast day.
We'll see you next podcast day. Thanks, everybody.